Yeah, so thanks for being here. And I'm going to talk about a somewhat provocative topic, though I think I will have much easier life after talks from yesterday from SAP, and in particular, surprisingly and coincidentally, talk just before mine. So I'm going to talk about accelerator-centric operating systems. And so, well, I'll start with the less of a provocative slide, saying that it's kind of hard to build systems today which are high performance and low power. And let me put it this way, it's always been hard, but it's much harder today. And the reason is that we're seeing this triple of forces pushing systems in opposite directions. You have hardware architectures going up in the sky with adding more and more interesting features, but those features get exposed barebone to programmers because system software just cannot keep up with the rate of introducing of these features. And so what you see is the developers are kind of pushing very hard, fighting software and hardware, and sometimes pushing in the opposite direction. So in order to understand that, I want to kind of give you an insight, or kind of my understanding why we're here, why we are seeing this kind of fundamental discrepancy, fundamental conceptual discrepancy between the hardware and software architectures today. So if we start from the good old days of early 2000, CPU was the center of the world. It basically concentrated all the compute capacity. It had most of the number of transistors, and all other compute devices, or I would say peripherals, also hosted some compute devices like microcontrollers, which mostly were fixed hardware logic, fixed hardware functions, and served for low-level operations like drawing pixels and moving heads in storage. Now, in terms of software, this is like the slide that you used to see in operating system 101. You have operating system kind of guiding the world and applications running on CPU, and operating system is very conveniently exposing high-level abstractions for CPU programs to access IO devices. All right, so that was in early 2000. What are we seeing now in hardware space today? Right, so as you can see, the situation kind of changed dramatically. Because CPU performance scaling ran out of steam, or is running out of steam, I would say, we're seeing more and more accelerators coming into the system. So you can see various kind of storage accelerators. You can see, oops, not found the virus. Okay, good. I hope that my presentation will not be contaminated with viruses now. So the network accelerators are doing any kind of network I/O acceleration, and also apparently GPUs are used not only for pixel drawing, but also for doing high performance parallel computations, and many, many others. What is really interesting, though, that you're not only seeing fixed function logic in all those devices, but you're really seeing more and more transistors spent on programmability. So those devices are actually very powerful, and they can run real programs. You can run programs on a multi-core storage accelerator. You can run programs, high-performance programs, on GPUs. And if you think, just count the number of transistors, turns out that CPU is no longer the top transistor count consumer. So it turns out the GPU is twice as large in terms of transistor count, comparing high-end GPUs and CPUs. And network adapter and storage accelerators are about 1 billion transistor, which is about a quarter of a modern high-end CPU. So, right, so you can see that the system is becoming more accelerator-reach and basically no longer CPU-centric. So what do you expect to see in the software, right? So it turns out that software hasn't changed much. Right, so what we're seeing is basically this good old operating system running on CPU and mediating CPU access to I/O devices. But surprise, surprise, all those devices, all those new accelerators, are basically exposed barebone. Right, they themselves, if they run any programs, those programs are real programs still, although they're accelerated programs, but they are running there, and sometimes they need to access networks, sometimes they need to access some kind of high-level services like files. So imagine your DSP or FPGA wants to access a file, right? That's kind of a problem. You really have to build a lot of software to do that. And I will show you later that it's actually not a simple task. Very tedious, I must say. So the real question that we should be asking is, we're having an accelerator-reach hardware systems, and we have a completely CPU-centric software. And I believe that that's actually the main problem that we have to solve in operating systems community. We really have to understand that our CPU-centric software architecture no longer viable, or at least needs to be expanded to something that is more suitable for today's hardware. And what I'm trying to do in my research, and that's what I'm going to talk about today, is how to extend operating system layers into the accelerators themselves and allow accelerator programs to effectively use all high-level services like networking and file system in particular, but also for network to access storage devices, for networking programs, for storage programs to access GPU, et cetera, et cetera. So you have this peer-to-peer architecture, and as you've heard, peer-to-peer communication between peripheral devices is actually supported by hardware. So really what we do need is the operating system support for that kind of hardware. And that's the vision of the operating system of the future, or of actually today, as I will show you some of the examples. On the left, you still have the good old operating system as you used to see before, but on the right, you have the operating system layers that are implemented on accelerators. And so in this talk, I'm going to talk about one particular case in point, which is a case in point for GPUs, right? And I will also explain why I choose GPUs as kind of the way to highlight the benefits of this architecture. So of course, I will only scratch the surface in terms of the details that I will provide today. Many more details are in those papers. Okay, so this is the outline. I'll be talking about what GPUs are very briefly. Then I will talk about GPUnet and GPUfs, which are those layers that basically expose native file system and networking services to GPUs. And last but not least, I will kind of recap with the main takeaways, main lessons that we learned while building those. Okay, so CPU, GPU systems are heterogeneous systems which host GPU connected to the CPU. GPU is this processor that has its own memory for efficiency, and CPU can talk to a GPU through this PCI Express bus in the bottom. Now, in order to run a program on a GPU, what you do is kind of you're using very standard coprocessor model. Assume you have a computation running on CPU, and it has its own state. First, you partition that state into some part that will be used on GPU for GPU computation. Then you take a part of computation, you parallelize it into many, many threads and run on GPU. This is called a GPU kernel. This function effectively is called GPU kernel. And once this function is over, you take the state from GPU, put it back into CPU, and that's basically the end of GPU use, right? So presumably this function will run much faster on GPU than on CPU. So this is standard standard coprocessor model, and it's been very successful, and that's basically the whole reason for doing research in GPUs to start with, because they do matter. They make real difference, and we can argue about how much difference they make in terms of speedups, but it's absolutely clear that they do provide a lot of benefits for a lot of interesting applications. Right, so there's a long list of applications that I can continue further, but what you are not going to find in this list are applications that we, me and you are using every day, right? For example, web search, web services, network services, antivirus, file search. Those are pretty parallel applications, and GPU is supposed, and was shown, to be very beneficial for accelerating them, but you're not seeing them in this list. Why is that? Well, in order to show you that building any application that involves I/O input-output on GPU actually is a very, very hard task, I will show you a simple example of building a simple GPU-accelerated server. So let's start with the baseline, right? The baseline is CPU server, and in CPU server, these are 3 lines of more or less 3 function calls that you have to do. You do receive, compute, which is presumably compute intensive, so you'd want to offload it to GPU, and then finally send. And receive and send calls are those nice socket API calls that you typically are exposed to. We learn in operating system classes. Now, what you would really want to see is more or less the same kind of code for GPU, right? So this GPU compute function is going to be very compute intensive and highly parallelizable, so you definitely want to run it on GPU, but all the other functions are apparently standard socket calls. Well, turns out it's really far from practice. So let me show you where it is that far. So first of all, take a look at this window on the right. It's going to grow because this is the window where all the code that we have to write in order to build this server will appear. So first of all, you accumulate the data in CPU memory, and then you transfer it into GPU. But it turns out that in order to transfer it efficiently, you really have to batch together, also because you want the GPU to work on many tasks together, first, and second, because sending little data every time is actually very inefficient. So you have to optimize data transfers. Then you invoke the GPU compute function, but turns out that when you invoke it, different requests can actually require a different amount of computations. So some requests will end before, and that will cause the imbalance, right? So that's the obvious downside of batching. You don't want to batch different requests. You want to batch requests that have more or less the same computation requirements. Well, after you figure that out, you go and really call the GPU compute function, and then you're happy that the computations are over, but now you have to clean up and bring all the data back, right? And at that point, you have to dispatch all the data that was batched before and send back the results to the clients. Well, I can imagine that this call is not super interesting, and it's not super hard. You can write it, definitely. What becomes harder is that when you realize that you really have to pipeline all these stages, right? And when you're going to pipeline them, you're going to write very nasty, multi-threaded code which is prone to lots of bugs, and you really have to use a lot of small tricks in order to make it efficient. So my point is that instead of trying to optimize this and trying to provide some kind of nice framework that many people actually are doing, let's step back for a second and kind of think, what are we having here, right? We are basically trying to force ourselves into working in an environment that has to be different, right? We are trying to build something to manage GPU on a CPU, but GPU can manage it itself. And think about it this way. If you had a CPU code, you didn't have to write all those. Why? Well, because operating system takes care of it, right? You don't care about buffers when you use sockets, right? You don't care about data transfers between network card and CPU. It just happens, right? All the pipelining just happens. And so that's exactly what I want to do. I want to have this kind of support for GPUs as well. And the way, that's the main takeaway point here, that is kind of the going through the presentation, is that GPUs are not coprocessors. They are pure processors, and they really need I/O abstractions. They really need high-level abstractions that, like CPUs, they can use in GPU code. So it's actually not only a theoretical kind of proposition. We actually built the system that allows you to use networking on GPU. That's what we call GPUnet. And as you can see, the green code is the code that is executed by the GPU. And it is fully compatible from the network perspective with the CPU code, with the CPU client and GPU client. So this server is actually running on GPU. Now, I hopefully convinced you that it's realistic, but I'm pretty sure that you're still not convinced that it's worthwhile. So let me show you from the programmability perspective. It is worthwhile because, first and foremost, CPU is not involved. So you don't have to jump between CPU and GPU logic in your program. You just run GPU code, right? You just write a single programming model. You don't switch programming models in the middle. Now, you don't have CPU involved here, and in practice, neither in either in control path or data path. So let's drop it from the picture. We don't have CPU in the system anymore. And another interesting benefit that you can get is that you don't need to work hard on all those optimizations that I mentioned, because the requests kind of get into GPU threads directly, and all the pipelining is made possible through having many, many threads and many requests handled in flight. Last but not least, of course, there is a little bit of, things that we have to do as system programmers, but unlike the previous case, only system programmers have to deal with that, right? So we really have to route all the performance optimization code and all that, but it's our job, right? It's my job, it's my interest, not the application developer, okay? So hopefully I convinced you that it really makes sense from the programmability perspective. What about performance? So in terms of the performance, you really can build a high-performance network library for GPU, but you do need network support, network card support. So that's where RDMA transport really matters. We do support for backward compatibility. We do support non-RDMA transport, but that would be less performant. Now, networking is just one point in this question, right? In this nice picture. Another point is a file system, and I'm only touching very briefly on the file system interface that we built. So as you can see, from the application perspective, all the CPUs and GPUs have access to a file system, and also they have system-wide shared namespace, so GPU can open file and update it, and CPU will see the updates. There is a POSIX CPU-like API and access to persistent storage, so everything that you would expect from normal file system support. Right, so how well does it work, right? So I talked about programmability. I only mentioned why, from the performance perspective, it would make sense, but does it really work? Well, it turns out, yes. So we built a real application with network, with GPU server. So this is like a standard 3-tier application where the first tier is a client. It passes some data to the compute server. This compute server queries the database and computes certain features and compares them and sends the result back. Okay, so again, regardless of what this application is doing, the fundamental structure of this application is no different from many other applications that are in use in many data centers. So what is really important here is that GPU server is indeed running on GPUs, multiple GPUs in fact, and communicates with the unmodified CPU database, memcached, and also unmodified CPU client. So how well does it work? No systems talk can be complete without some kind of nice graph, right? So this is the nice graph that I have. This is a latency throughput graph where throughput in the bottom, you want to have very low latency and super high throughput. That's your goal. That's the right bottom corner. And you don't want to have high latency and low throughput, apparently. So if we compare several designs and several implementations of this server, we can see that the GPU server, GPU accelerated server, using the standard kind of out-of-the-box GPU programming, it doesn't really reach even the performance of a single CPU. But when you take GPUnet and you implement your server with GPUnet, then you get substantial performance improvements both in latency and throughput. What is more important that even when compared in terms of the programming complexity, and lines of code is kind of nice proxy, you can see that you get the same server running on GPU with 50% of lines of code versus the CPU server. Okay, so that was all nice. Hopefully I convinced you that building accelerator-centric services makes sense also from programmability and performance point of view. But I'm pretty sure that people in the audience kind of still question the fundamental motivation for this, right? So let's say tomorrow we have hardware that is absolutely cache coherent, you have this nice CAPI API, you have new hybrid CPU-GPU architectures. Why do you need operating system on this, right? So first of all, I don't know. Well, we never tried. We are just working on it, so I don't know whether we really need it. But I believe we do need it. And the reason why is that there is a gap between these two different worlds of CPU and accelerators. And this gap comes into play in hardware interaction overhead, in programming model gap, in I/O and memory performance gap, in I/O topology. You know, you may have different kind of accelerators, different kind of GPUs in the same system connected in different ways. And in the very end, in order to squeeze the last bit of performance, you as a programmer would have to deal with all those low-level details. And I believe that that's just plain wrong, you know. I like those. You might be not, okay? So, right, so this vision is indeed still vision, you know. We have only one point in the design space. We tried only one single sample point, right, which is GPUs. But there are kind of common challenges, not only for GPUs. It could be for FPGAs, it could be for other architectures. And some of them are that, indeed, the hardware of those accelerators was not built with providing operating system functionality in mind, right? So you have to work around this. And it seems that by working around this, what we're doing is we're basically understanding what are the real requirements for the hardware to support those hardware, those operating system services without having to change the hardware, you know, bottom up and basically reinvent the CPU virtual memory, CPU interrupt system, and all that. What is also interesting that when we started to implement those services on GPUs, we figured out that although you have the data basically injected into GPU, it might become completely unusable. The reason is that GPU is, after all, accelerator, right? So there are some operations that you have to basically do in order to prepare the data to be GPUable, right? And turns out that when the data is injected into the GPU directly, well, that's no longer the case. So you really have to have some logic that does some data transformations in flight, and that's basically what what we are pursuing now. So to recap, what I showed you and hopefully convinced you that we are experiencing a kind of paradigm shift in terms of what kind of devices, what kind of hardware architecture in a compute node as a whole we are seeing today. And I try to convince you that accelerator-centric operating system architecture makes sense, and both from programmability and performance. And, you know, going back to the first picture, you know, in terms of speed, I want this car to move faster than just, you know, than just with all those gentlemen pushing it. But also, in the very end, you know, I really want to speed it up. So I think that this kind of architecture has a future and has a merit to effectively push systems into much faster gear. Coming up next, we are building distributed applications that are entirely accelerator-based, not using CPU, or at least trying not to use them as much as they can. We are building high concurrency servers on GPUs and FPGAs. We're building a multi-accelerator support. Turns out, you know, GPU memory is small. You need to have much more. You need to access CPU memory. And you have a lot of work on the operating system layer to figure out how to do that right. Of course, there are some kind of fundamental issues that we need to solve, like building virtual memory support for devices that don't have page faults, kind of introducing memory consistency that is optimized for I/O, for accelerators, various kind of isolation and security issues that apparently cannot be supported out of the box by these devices. Last but not least, we are really going further with the hardware involving other accelerators and other applications that would benefit from peer-to-peer support and accelerator-centric operating system design. Of course, this work has been a teamwork, and I have been working with wonderful students here at the Technion, and also collaborating with Emmett Mitchell's group at UT Austin. So let me conclude by saying that I do believe that accelerator-centric operating system design is the design of the future, and I would be happy to take questions. Thank you.